So in this section, we're going to talk about variables and expressions. Now, in previous courses of math, you've probably seen expressions before. Now, for example, we'll take the expression 3x squared plus 5x minus 7. Now, this is an expression that really stands for a specific number. Now, all expressions stand for a specific number, and that number depends on what number you pick for the variable, which in this case is x. This is called the variable because it's varying. So we can plug in any number within our domain for x, and you'll get a different number resulting from the expression. Now, the other numbers that are in this expression are called constants. That would be 3, 5, and 7. Now, these are called constants because they're not changing. So, the expression, or the value of the expression also depends on these constants, but they're not going to be changing. So in this section, we're going to talk about evaluating expressions and some of the tools that we can use to evaluate them by simplifying using the field axioms that we talked about in the previous section. Now, a variable is a letter that we use in expressions that stands for an unspecified number from a given set. Now, this set can be restricted by what's called the domain. The word domain comes from the Latin domus, meaning house. So the domain of a variable is, in a sense, like where it lives, what it can be. So let's say we have the domain digits, and this is the notation using braces that we use for domain, digits. Then x in this domain can be 0, 1, 2, all the way to 9. So in this book, we've made the agreement that unless the domain is otherwise specified, then the domain for all expressions is going to be all real numbers. Now, if they specify differently, then you must treat the domain accordingly, but if not specified, it's going to be all reals. Now, an expression is a collection of variables and constants that are connected by operation signs, pluses, minuses, multiplication symbols, division. So, and these expressions stand for a specific number. So, and again, to find out what number the expression stands for depends on what number you plug in for the variable. So, for example, let's say we have the expression again, 3x squared plus 5x minus 7. Now, we're going to evaluate that expression if x equals 4. So, to do that, we're going to plug in 4 for whenever we see x. So, we're going to multiply 3 times 4 squared plus 5 times 4 minus 7. The parentheses stand for multiplication. So then, to simplify, we're going to have 3 times 4 squared, which is 16, plus 5 times 4 minus 7. And then 3 times 16 is going to equal 48, plus 5 times 4 is 20, and minus 7, which is going to equal 61. So, when we plug in 4 to this expression, it has a value of 61. So, the way that we arrived at this answer depended on a few certain things. First, you have to realize that when we're evaluating the expression at x equals 4, we need to plug in 4 for whenever you see x in the expression. The other thing is that the value we obtained depended on the order that we performed the operation. So for that reason, so there can be some agreement in the math world that they developed the order of operations, which you might know previously as PEMDAS. So there's a little acronym to remember the order of operations, and that is called PEMDAS. And the P in PEMDAS stands for parentheses. then exponents, then multiplication, division, addition, and subtraction. So what this is saying is when you're given an expression, you do what's in the parentheses first, starting with the innermost parentheses, then evaluate the exponents. Now, multiplication and division are more or less the same thing when you think about it, because multiplication, let's say we have x, like multiplication obviously is just x times y, but if we have division, x divided by y, that's really the same thing as x times 1 over y. And the same thing with subtraction. Obviously, if you have x plus addition and subtraction, obviously if you have x plus y, that's going to be like addition, but x minus y is really the same thing as x plus the opposite of y. So, with that being said, after evaluating the exponents, you multiply and divide at the same time, but from left to right. Then you add and subtract at the same time from left to right. So now we're just going to go through some examples talking about or evaluating expressions with the order of operations. So first, let's look at the example of 3 plus 4 times 5. Now, the reason we have order of operations is because the order in which you perform this expression is going to change the answer. So, order of operations says that you do multiplication before you do addition. So this is going to be 3 plus 4 times 5 is 20, then which is going to equal 23 because you add less. Now, if we had not followed that, and we had done addition first, then we would be left with 7 times 5 if we had added first, which would have gotten us 35, which is a different answer. So that's why we have order of operations. Okay, so let's look at another example. Let's say we have 3 plus 4 times 5 divided by 2. Now, order of operations states that for multiplication and division, you perform that before addition and subtraction, but you multiply and divide from left to right. So that being said, we'll start with from left to right. We don't add first, so we're going to leave the 3 plus, then 4 times 5 is going to be 20, divided by 2. Then we're going to divide, which will be 3 plus 20 divided by 2 is 10. So the answer, and then we add, so the answer is 13. So we're just going to take a look at one more example. That's going to be 3 minus 4 times 5 divided by 2, plus 9. Now again, PEMDAS in the order of operations states that we multiply first and we multiply and divide before adding and subtraction, and we adding and subtracting, and we do so from left to right. So it's going to be 3 minus, then 4 times 5 is 20, divided by 2, plus 9. Then we divide, so that will be 3 minus 10 plus 9. Then we add and subtract from left to right, so that will be negative 7 plus 9, which will be positive 2. So the last thing we're going to talk about is absolute value, because an expression might contain the absolute value operation. Now the symbol for absolute value is given by these two lines outside the number. Now this means the distance of x from 0. So it's always going to be a positive value because it's a distance. So for example, if we have the absolute value of -3, the distance of -3 from 0 is going to be 3 units away, so that's going to equal 3. Now the absolute value of +3 is also 3 units away, so that will be +3. So this can also be shown on a number line. So if we draw a number line, and we're going to say this is 0, and we have 1, 2, 3, and -1, -2, -3. +3 is 3 units away from 0, and -3 is also 3 units away from 0. So that's why they're equivalent. Now, if we're taking the absolute value of x, this kind of presents a problem, because if x is a positive number, then obviously the absolute value of x is equal to x. But if x is a negative number, then the absolute value of x is going to be equal to the opposite of x. For example, let's say that x equals 9, or x equals -9. Then the absolute value of x is going to be substituting in for x the absolute value of -9, which is going to equal 9, the opposite of x. So all you really have to remember is the absolute value of x equals x if x is positive, but the absolute value of x equals the opposite of x, negative x, if x is negative. So now we're going to look at a couple examples using the field axioms to simplify expressions and make it easier to solve. So we're going to start with the expression 2, oh geez, forgot to switch to the pen. Okay, 2 minus, then we have parentheses, 3 times x minus 2 minus 5 times parentheses x minus 1. Now you should notice that there are two different versions of parentheses that are being used here, and that's because we want to indicate that there are multiple parentheses within parentheses. So the order that we do this is, for the innermost parentheses we'll use actual parentheses, then the next and the outermost and the next outer things we would use called brackets, and finally outside of that we would use what are called braces, also used in set notation. Now, you should also notice that some people don't want to use all these different symbols, so they'll just use multiple parentheses around each other. But in any case, the order of operations and the field axioms say that we can distribute, but we will deal with the innermost parentheses first. So to do that, we're going to have 2 minus 3 times parentheses x minus 2. Now we're going to distribute the -5, so we're going to have minus 5x and plus 5. Then we're going to combine like terms within the parentheses. So we're going to have 2 minus 3 times x and -5x combines to make -4x, and minus 2 and plus 5 combine to make plus 3. Now we can distribute the -3 into this, so we're going to have 2 -3 times -4x is going to be plus 12x. -3 times +3 is going to be -9. And now, combining like terms again, we're left with 12x minus 7. this is going to be the simplest form of the expression. Now these expressions are completely equivalent to each other, and that's why we call it simplifying, because we're creating a simpler form of the expression. So this concludes our lesson on expressions and variables. Now all this information can be found on pages 9 through 13 in your textbook. So if you want to go over either, the order of operations or simplifying expressions, there's example problems there that I went through, and you can follow along there. And if you get stuck, just go back and remember the field axioms. Those can be very useful when simplifying expressions. And of course, the order of operations. So good luck.